In the last section, we learned two different operations we could do with vectors. We did vector addition, where you add two vectors together to get another vector. And we did what's called scalar multiplication, where you just multiply a vector times a number to get another vector. In this section, we're going to introduce what's called the dot product. So this is our first kind of multiplication that involves two different vectors. So when you perform a dot product, you're going to end up with just a number. And the way you calculate that number is you multiply together the x coordinates of the vectors, and then you add that to the product of the y coordinates from the vectors. Okay. Now before we do some examples, I do just want to mention some properties of the dot product. For the most part, this is going to work the way you expect. Regardless of the order you multiply, you'll get the same thing. If you multiply by a 0 vector, you get the 0 vector. Okay. If you want to try to distribute your dot product, great, you can do that. If you dot product a vector with itself, then you actually just get the magnitude of the original vector squared. So this one is perhaps a little bit new and surprising. That can be useful. And then also, if you wanted to distribute just taking a number times a dot product, it doesn't really matter when you multiply by the number. Okay, so let's do a few examples of this. So just some basic dot product calculation. I'm going to take the x components and multiply them together. So that's 3 times 4. And I'm going to take the y components and multiply them together. That's 5 times 2. So 12 plus 10, I'm getting 22. Similarly on this guy, take the x components and multiply together. Take the y components and multiply them together. That's 0 plus negative 18. Getting negative 18. So dot products are pretty straightforward to calculate. Just remember you're going to get a number for your answer, not a vector. I want you guys to go ahead and see if you can calculate these 4 answers based on what we've already learned about dot products, and maybe using some of those properties as well. So see what you can do with these, pause the video, then unpause and see if we got the same thing. So let's start with the first one, u dot v, then multiply that by w. Okay, using our typical order of operations, I need to do the stuff in parentheses first. Okay, so I'm going to dot together u and v, so negative 2 times 4, plus 3 times 1. And that's still supposed to get multiplied by w. So let's see, that's negative 8 plus 3, so negative 5 times 3, 0. So now if I multiply each component by negative 5, I get negative 15, comma 0. Alright, let's look at part B. It doesn't matter when I multiply by 2. So I could do it exactly as it's written here, where I find 2u and then dot with v. Or I can multiply by 2 at the end, so it's kind of up to you. We have some choices. I'll just do it exactly the way it's written. So I'm going to do v, that's 4, 1, dotted with 2u. Let's go ahead and simplify 2u. 2 times negative 2 is negative 4. 2 times 3 is 6. Sorry, didn't mean an equal sign there, a dot. And now let's do the dot product. 4 times negative 4 plus 1 times 6. That comes out to negative 10. Alright, magnitude of v. Okay, this is just a basic problem like we would have done in the last section. So it's going to be the square root of the x component squared plus the y component squared, which comes out to the square root of 17. Now the reason we did that is so that I could calculate v dot v. There's two ways I could do this. I could actually just dot v with itself, or I could know that it's just going to be the magnitude of v squared. So in other words, the square root of 17 squared, which is just 17. Okay, it's also possible to use this property in reverse. If I dot a vector with itself, if I want to find the magnitude, just take the square root of that number. Okay, so that can be kind of a useful trick to move back and forth between magnitude and the dot product of a vector with itself.